Assalamualaikum and good day to all of you. This week we will start our discussion on the introduction to fluids. Okay, now let's get started by asking the most fundamental question, which is what does it mean by fluids? Okay, fluid is a substance that can flow. Okay, it includes liquid and gases because both of them can flow. But here in this topic, I will only cover liquids, not gases. Gases we will cover next semester, inshallah. So although gases is different state of matter, but it can also be put under or known as fluids because it can flow. Okay, now what is fluid mechanics? Fluid mechanics is a study about fluids, and it can be divided into fluid statics or hydrostatics, and secondly can be divided into fluid dynamics or hydrodynamics. Okay, as its name implies, fluid statics is study about fluid when it is at rest. Okay, it is not moving, the fluid is not moving, not flowing. And fluid dynamics is a study about fluid that move or the flow of fluids. Okay, the next terminology that is important in this topic is hydraulics. Okay, hydraulics deals with the mechanical properties of liquids, emphasizing on the engineering uses of fluid properties, meaning it is more on application. When we mention the word hydraulics, you have to remember, put it in your mind, it is on the application, okay, the use of liquid properties for our own benefit. So usually we do hydraulics is about pumps, okay, pipe flow, turbines, hydropower, flow measurement, and etc. Or in a biological related application, it is about heart valve function, blood flows, wave dynamics, and so on. Okay, and this is the example of heart valve functions, blood flows, pipe flow, turbines, and pumps, and sedimentation transport. Okay, sedimentation transport is when in the river we have this debris, okay, the kotoran debris at the bottom of the river or in the ocean at the bottom. It is sedimentation transport, meaning this debris, okay, or small rock can be transport or moving by the flow of water. So this, all of this application or all of this uh, function, heart valve, wave function, blood flow, all can be said fall under the topic of hydraulics, meaning the application of fluid mechanical properties of liquids, okay, of fluids. Now let's take a look at physical properties of fluid. Okay, there are several, but we will only look at two. Okay, the first one is compressibility. Okay, it is the ability of liquid to be compressed, and this compressibility is depend on particle shape, particle density, hardness, chemical composition, and particle size. So which means different type of liquids will have different compressibility. Okay, second one is viscosity. It is a measure of fluid's internal resistance to move or flow, which means in easier words, it is how easily fluid flows. Okay, how easily fluid flows. So that refers to viscosity. So remember, compressibility and viscosity are the physical properties of fluid. Okay, viscosity is also known as resistance of a fluid to change in shape or deform. Okay, how difficult it is to make it flow or to change the shape or size or make it deform. Okay, so this is the example of how fluids can be compressed. So different fluids will have different compressibility. So it all depends on the type of fluids, because different type of fluid will have different particle arrangement. So it affects the compressibility. Now let's look at example 1. Okay, do you know that in our brake system in the car or lorry, okay, we use fluid or liquid in the system. Okay, here we put our foot or step on the brake, so our force will be transferred, okay, to the whole fluid, and later on at caliper here, okay, it will clutch or hold the rotor here. So this rotor here is at your tire. So this you have learned at school in Pascal law, how force is transferred via fluids. Okay, how force is transferred via the fluid. So the question is, will my brake be more effective if I use less compressible liquid? Is it better for your brake to use less compressible liquid or not? Okay, think about it. Now, example 2. Okay, which one has higher viscosity? Okay, which one between the left picture or the right picture? Okay, let's imagine this is your ordinary plain water, your drinking water, and on the right side is your honey, madu. Which one has which one has higher viscosity? Okay, so we say your honey on the right side has higher viscosity than the drinking water. Okay, because honey, based on this picture, this visual, we can see that it is slightly difficult, okay, more difficult for it to flow compared to our drinking water. Okay, now let's look at types of fluid. Okay, the first type is known as ideal fluid. Okay, so ideal fluid has characters. Okay, the character is, it is first one, it is incompressible, cannot be compressed, and second is it has no viscosity. Okay, the third one is the fluid motion is steady, which means velocity, density, and pressure at any point in the fluid do not change in time. Okay, number 4, fluid move without turbulence. Okay, what is turbulent? I will explain later. Okay, and it is also called imaginary fluid because it does not exist. We create this category because we want to create theory. So in order to create theory, usually we assume there is ideal condition. Okay, so here in this case it is ideal fluid. This is the first type. The second type is known as real fluid. Okay, real fluid has opposite characters compared to ideal fluid. So it is compressible, it has viscosity, and all fluids are real. Any fluids around us are real. Okay, this real fluid can be further divided into Newtonian and non-Newtonian. Okay, so what does it mean by Newtonian and non-Newtonian? Okay, let's look after this. Okay, now let's look at the example or the meaning of Newtonian and non-Newtonian fluid. Okay, so imagine you have a cup or a bowl of water. Okay, you put water in a bowl and imagine you punch the water or you dip your hand. So there is no problem, right? We can do this anytime. Okay, no problem. You will have no problem of punching the water, the surface of water. Okay. And let's look at this picture. Okay, this guy, no problem dipping his hand, But if he tries to push a force, okay, punch the fluid there, he cannot, okay, because suddenly the fluid become hardened, okay, mengeras, suddenly, okay. If he use no force or just dipping his hand, he can. But if he punch, suddenly the fluid become hardened, okay. So the left one we call Newtonian, okay. On the right hand one, the right side, we call non-Newtonian, okay. So Newtonian fluids obey Newton's law of viscosity. So we say the viscosity is constant, independent of shear rate, okay. Whereas for non-Newtonian fluids, it does not follow Newton's law of viscosity. You see, viscosity is not constant, okay. When he touch, the viscosity is like that. But when he punches the fluid, suddenly it become hardened. So we say viscosity is not constant and is dependent on the shear rate. Okay, here both of them have this shear rate. Okay, what does it mean by shear rate? Okay, shear rate is the rate of change in velocity at which one layer of fluid passes over an adjacent layer. Okay, I will further explain the next slide. Okay, now let's look what does it mean by shear rate. Okay, because we have seen that the guy that tries to punch the non-Newtonian fluid on the surface, he couldn't do that because suddenly the surface become hardened, mengeras, meaning the viscosity change. Because there is difference in shear rate, the viscosity change. So what does it mean by shear rate? So we know that what is shear stress? Okay, we know this. Okay, last week we have learned. Okay, shear stress cause things to shear like this. Okay, menyengit macam ni. Meaning here it is not moving. The down part. Okay, let me show. The down part here is not moving, but the upper part is moving. So it cause it to menyengit macam ni. This is shear stress. Okay, so in this case, it is also like that. Okay. Okay, imagine this is your non-Newtonian fluid. We divide it into several partitions. Okay. Suddenly imagine you punch your hand. Okay. You punch the liquid. Okay, the non-Newtonian fluid here. So your force will hit area 4 and area 5. Okay, without 3, 2, 1 and 6, 7, 8 moving. So it creates situation like this because here it creates situation like the shear stress here. This part is not moving, only the upper part is moving. So here the partition of 1, 2, 3 and 6, 7, 8 is not moving, but 4 and 5 is moving. So we say that layer of fluid 4 and 5 move faster compared to their adjacent layer because this move faster. Okay, so the viscosity suddenly change because there is difference in the shear rate. So we say that the viscosity of non-Newtonian fluid, it depends on the change of your shear rate. Okay, when there is change in shear rate, the viscosity will change. Okay, that is for non-Newtonian fluid. For Newtonian fluid, it will not change. The viscosity will remain the same. Okay, no matter how high your shear rate is. So shear rate in word is the rate of change in velocity at which one layer of fluid passes over an adjacent layer. So here 4 and 5 because it moves faster than 1, 2, 3 and 6, 7, 8. So the viscosity change. Okay. This is the specialty of non-Newtonian fluid. Okay, our another example. Okay, this is for just general knowledge, not in your syllabus. It's called Weissenberg effect or rock climbing. It will only happen to non-Newtonian fluid. Okay, you will see that after some time, the yellow liquid will climb up the rod. The rod is rotating, yeah? Rod is rotating, and your fluid will climb up. Okay, fortunately, in this topic, I will cover only ideal fluid. Or maybe, so we are happy, yeah? Only small part of fluid. Or maybe it is unfortunate because we will only cover ideal and not real fluid, not non-Newtonian fluid, okay? Only ideal fluid. Since we know study of fluid can be classified into fluid statics, okay, and fluid dynamics, so there will be several laws that we will study under both of these uh, category. Okay, under fluid statics, we will learn about buoyancy and Archimedes Principle, whereas under fluid dynamics, we will learn about flow rate, equation of continuity, Bernoulli's principle, viscosity, Poisson's law, and Stokes' law. Okay, now let me introduce to fluid statics or hydrostatics. First thing you have to know about fluid statics is, okay, whenever there is a body or material or substance, when we put it underwater, okay, this material or body or substance will experience pressure exerted by water. Okay, the direction of pressure, okay, it will exert pressure at right angle, meaning 90 degree to the body surface. Okay, so it means it has, we can say it has no pressure. It will attack whole body or material or your substance from any point. Okay, and the direction is 90 degrees or right angle to that surface. Okay, now let me introduce something about fluid dynamics. Okay, fluid dynamics is about flow of liquid. Okay, so imagine you have water, okay, flowing in a pipe here. Okay, flowing in a pipe here. Okay, we can draw an imaginary line here, so many line here, okay, indicating the movement of the particle, the water particle. Okay, this is just, this line is to show the movement of the water particle. Okay, so we can see, since there is many line here, we say it is layers in flowing fluid. And here, when a liquid flows through a pipe, okay, the path of any particle here, meaning this line, the path, we call it streamline. Okay, so to make it easier, we only draw few lines. But if it depends on the size of particle, there will be million or billion of lines. But for analyzing, we usually draw several line only. Okay, so in different type of pipe, we can see this is how we draw it. Okay, is streamline. Okay, as long as the line is not intertwined or berlanggar, okay, disturb other line, we call it streamline. Okay, okay, under fluid dynamics, okay, the flow of the fluid can be described into two categories. Okay, laminar and turbulent. Okay, what does it mean by laminar flow? Okay, laminar flow is like this. Your line, our line here that we draw, okay, is like this, meaning the line is not disrupting other line, it's not intertwined, tidak berlanggar line lain. Whereas for turbulent flow, is like this. Okay, this line suddenly comes down. Okay, this line intertwined with other line. This is turbulent flow, this is laminar flow. Okay, this is the definition of laminar and turbulent. Okay, laminar flow, also known as streamline flow, occurs when a fluid flows in parallel with no disruption between layers. the flows are smooth and steady. Okay, like this. No disruption or intertwine between the line. Whereas turbulent flow occurs when a fluid flows violently, okay, with disruption between layers. Okay, now let's proceed with buoyancy and Archimedes principle. Okay, this topic supposed to be taught tomorrow on Tuesday, but since tomorrow we have public holiday, Maulidur Rasul, so I have to teach you today. Okay, what is buoyancy? Okay, buoyancy is upward force or thrust on a body immersed in fluid. So if things is immersed in fluid, there will be weight pulling it down and upward force or buoyancy push it up. Okay, so things afloat due to buoyancy. So ship, boats, anything that floats on the water, in the water, it is due to buoyancy. Okay, and it can be elaborated by Archimedes principle. Buoyancy can be explained by Archimedes principle. Okay, there are three different cases of buoyancy. Okay, the first one is like this. Okay, you see things sinking in the water. Okay, in this case, we say weight is more than buoyancy, meaning in this case, density of object is more than density of liquid. So things or your box or anything still, okay, it will sink into the water, okay, right to the bottom of the water. Okay. For second case, okay, we can further classify it into the first case is okay, buoyancy more than weight. Okay, imagine you throw something into the water. Imagine you throw this red box. Okay, imagine you at first you throw and you throw very hard that it goes deep into the sea. Okay, now because it has, let's say, the density is less than the density of the water, okay, then the box will go up after certain depth, then it will stop and go back up. Okay, the movement of going up, going to the surface, during its motion, during its moving to the surface, we say that buoyancy is more than weight. That's why it can move up, because at that moment, during its moving up, the buoyancy or force upward is more than weight. Okay, but when it reaches the surface and floats, we say that buoyancy force is equal to the weight. So be clear. The first case is when you throw into the water and it go to certain depth and then it move up to the surface. Okay, the ongoing process moving up at that point is buoyancy more than weight. But when it reach the surface and floats, the buoyancy equal to the weight. And in this case, when things float, we say density of object less than density of fluid. The third example, imagine your submarine. Okay, submarine is very special because it can control its density. Okay, how? Because it can pump the water in, pump water out from its body. So by doing that, it can change the density, thereby it can submerge and then it can go up, it can go down, okay, due to the change in its density. Okay, in this case, we say that buoyancy equal to force. So it can go to any depth that it want by adjusting the density, by adjusting its density. So in this case, like this submarine stay here, we say that density of object equal to density of fluid at this depth, okay, at this level, at this depth. So buoyant force is always present, whether the objects float, sink, or suspended in a fluid. There is always buoyant force. The thing is whether the buoyant force is bigger than the weight or smaller than the weight. Okay, if buoyant force is bigger than the weight, so it will push the material to go up. If the buoyant force is small compared to its weight, then things will sink to the bottom. Okay. Okay, since we say that buoyancy can be described by Archimedes Principle, now what is Archimedes Principle? Okay, imagine we put a tennis ball into the water here. Now the gravity is pulling down, which is the weight. Okay, the weight, and then we have up thrust. Okay, thrust going up because of buoyancy. Okay, now the force here is weight and thrust or buoyancy. Same thing. Thrust, buoyancy is the same thing. Okay, so the definition of buoyancy, Archimedes principle is this: the upward force or thrust or buoyancy. Okay, the upward force on a body immersed in a fluid is equal in magnitude to the weight of the fluid displaced by the body. So this is definition of Archimedes principle. If I ask you in exam, you have to write like this. Okay, write like this. So how to calculate upward force? How to calculate thrust? How to calculate buoyancy? Same thing. Upward force, thrust, and buoyancy, same thing. Okay, imagine because it says here that the buoyancy is equal to the weight of fluid displaced by body. Okay, when you put something in the water, definitely water will be displaced. Okay, just imagine you jump into the swimming pool, so the water will spill off of the swimming pool because you jump into it. So when you stay in the water and when you are in the swimming pool, the level of water will go up. Okay, that volume or mass of water is that goes up is equal to your buoyancy force. Okay, so imagine here you have 5 kilogram bar of, let's say, metal here or cube, 5 kilogram. Okay, when you put in the water, water will be displaced. Okay, so if we can measure the weight of water displaced, and let's say we get 2 kilogram of water displaced, so this is if we measure we time with 9.81. Okay, this is your buoyancy force. Okay, water or weight of fluid displaced is equal to our buoyancy force. So here upward force or buoyancy is equal to weight of fluid displaced. Okay, and of course in this case it is very easy lah because we can measure the weight of the fluid displaced. But in many cases we cannot, so we have to use some calculation to measure the weight of fluid displaced. Okay, now still the same picture as the previous slide. Okay, let's say we have an object. By using the weighing machine, we can get the mass is 40 kilogram. But now when we submerge it in the water, since we know that anything that we put in the water, there will be buoyant force equal to the weight of the liquid displaced. So because of this buoyant force, the reading now become 30 kilogram. Okay, this reading 30 kilogram, we call it as apparent mass. Apparent mass. This one is real mass. Okay, this one is apparent mass. So if we times this with 9.81 and this one with 9.81, so we get this is apparent weight. Okay, this is apparent weight, this is real weight. Okay, so what does it mean by apparent weight? Okay, apparent weight is equal to sum of true weight, okay, this weight, please correct this, also known as real weight, minus buoyant force. So why minus? Okay, this minus here because there is force pushing up, weight is pulling down, follow the direction of gravity. Okay, So minus buoyant force, so we will get apparent weight. So make sure you know the difference between real weight and apparent weight. Okay, apparent weight include buoyant force in the weight. So because buoyant force is different direction than gravitational acceleration down, so the mass or the weight will be lesser for apparent mass and apparent weight. Okay, imagine this picture of ships floating, of course floating in the water. Okay, now we know that weight pulls down. Weight will because of gravity, everything will go down. Or if we put in the sea, things will sink. But why sometimes things can move? Because there is something that balance the weight. Okay, weight is pushing down. Okay, but there is some force pushing up, known as buoyancy force. Okay, but where does this buoyant force come from? Okay, it comes from because water pressure pushes it up. Okay, remember I've told you anything that is put in the water, there will be pressure in every direction. Okay, remember back. Okay, in the introduction to liquids. Okay, uh, under the in the almost final slide. Okay, I say that anything that is submerged underwater, okay, there will be pressure exerted at on any direction, in any direction. So this water here, there is pressure pushing it up. So buoyant force actually come from water pressure. Okay, water pressure. So water pressure pushes these ships up, and it balance with the weight pulls down. So buoyant force come from water pressure. Okay, now since we know that buoyant force come from pressure, now let's see how buoyant force can be derived from the concept of pressure. Okay, imagine we have a container of water. Okay, let's say this is the container and fill up all by water until fully fill up by the water. Okay, now imagine we put something in here and it submerged. Okay, this rod. Okay, rod shape here is submerged. Okay, it is not fully sinking, but it is suspended in the middle like this. Okay, now we know that, okay, because in the water pressure will come from every direction, from here as well, and from below. Okay, right here. Okay, so because we also know that pressure is dependent on the depth. Okay, our the deeper we go, the higher the value of pressure. So we know that pressure here, because it is deeper compared to here. Okay, pressure here down here is higher than here, but here the pressure here is equal to this pressure because the depth is the same. Okay, the depth is the same, but here there is some difference. Here is higher than here. Okay, and I hope by this time you already know why the direction is downward, and sorry, this is downward and this is upward, because in the water pressure will be exerted from any direction. Okay, remember back our introduction to fluids lecture. Okay, now from here we can find difference in pressure, which is we take the bigger one. Okay, bottom, B stand for bottom, minus pressure at the top. Okay, so we get some value of difference in pressure, and because we have learned that pressure equal to F over A, F over A, so we can also write, okay, force equal to PA. Okay, so buoyant force actually is related to pressure from this formula. Okay, use this formula. Okay, now difference in force, okay, difference in force here to here is equal to force at the bottom minus force at the top. Okay, bottom push upward, top push downward, because downward is higher. Okay, so we expand the formula using this relationship. So FB now become PB, pressure at the bottom, times A. A is the area of the bottom of this rod. Okay, and PT, pressure at the top, times A. A is also here. Okay, area of the top, at the top. Now we expand, we rearrange the formula, making it look like this. Okay, and then from here, okay, we can expand from here to here because we know the relationship of here. Okay, V equal to H times A, equal to volume, height, or the height times area equal to volume. So we get V equal to HA. So now based on this, H equal to HB minus HP times A. So with this relationship, we substitute to here. Okay, that's why we can expand this formula into this formula. Okay, please take a look at this formula and try to understand it from every step of it. Okay. Okay, so this is the summary of all the formula that we have derived in the previous slide. Okay, please make sure you understand every formula here, and please go back and look through it. Okay, make sure you understand. Okay, but why this formula is important? I'm sure you maybe think that to calculate the buoyant force, what we need to know is just the displaced, the weight of the liquid displaced, right? That is equal to buoyant force. But why this formula and what we have learned is important? Because we want to relate the pressure to buoyant force, or I mean how buoyant force formula can be related to the pressure. Okay, the relationship is important. Okay, so that we can connect these two concepts. Okay, pressure and buoyant force. Secondly, okay, first is to understand, okay, relationship of buoyant force to pressure. Okay, secondly is this formula, all of this formula is important. Let's say if the question would like to know the depth of, let's say, this box. Okay, what is the depth of this box in submerged in water? So if we do not understand this formula, we cannot find the depth at which this box is suspended in the water. So now using this formula, we can easily calculate the depth at which this box is suspended. Okay, and make sure the density here refer to density of fluid, and area here is area of this box. Okay, please go back and look carefully of this formula. Okay, now the next topic is fraction submerged. Okay, what is fraction submerged? Okay, imagine we have iceberg here. Okay, now, okay, the volume under the water is indicated by this yellow arrow. Okay, so if on the surface we can only look at this iceberg on the surface, but below it, underwater, there is more of it. So we want to know fraction submerged, meaning the ratio of here to the whole volume. Okay, fraction submerged. So now fraction of object submerged is equivalent to, okay, volume submerged, okay, not submarine, submerged, divided by volume of the whole object, or in this case iceberg lah. Okay, so as we know, for floating, okay, weight of object, in this case weight of object equal to weight of fluid displaced, which means weight of the iceberg equal to buoyant force. Okay, BF is buoyant force for floating, right? FB, buoyant force, equal to the weight. Okay, the same statement here. So now that is weight. So if we weight, we know mass times gravity. So for mass of object equal to mass of fluid displaced. So just divide this part by gravity, we get mass. Okay, now volume submerged, okay, volume submerged is equal to volume of fluid displaced. Okay, this is common sense. Volume things that is submerged equal to volume of fluid displaced. Okay, now we label volume of displaced as FL dot DIS, fluid displaced. So in order to find fraction submerged or volume submerged divided by volume of the whole object, so we just take volume of fluid displaced divide by volume of the object, the whole object, because volume submerged equal to volume of fluid displaced. Okay, try to digest this part. If you don't understand, after this, go back and try to read this three part. Okay, these three equation. Make sure you understand, then only proceed to this equation. The key is here. The key is here. This part, this part. Okay. So now, since we know that density equal to mass divided by volume, okay, so volume of submerged divided by volume of object, okay, volume submerged divided by the whole volume equal to mass of fluid displaced divided by, okay, density of fluid displaced, okay, here, okay, using this relation we can get this relation. Okay, so volume of object, okay, we convert here like this. Okay, mass of object divided by density of object. Just use this relationship. Now, since the object floats, okay, the mass of the object and that of displaced fluid are equal. Okay, here, because it is floating, mass of object equal to mass of fluid displaced. So mass of object cancel with fluid displaced. Okay, like that. So they cancel from equation. Now become, okay, fraction of submerged, this part equal to density of object divided by density of fluid displaced. Meaning, if the question gives you the density of the object and the density of water or liquid, then straight away plug in the value of density into this equation. Now we can get fraction submerged or volume submerged. So fraction submerged is also known as volume submerged. Volume submerged. Okay, now let's look at the example. Very simple. Okay, we have 80 kg man floats in fresh water with 90% of his volume submerged underwater. Calculate his density. So just apply the fraction submerged formula. Okay, fraction of volume submerged formula using this. So just play around with the formula, you get, okay, this density. So this is density of the man. Okay, so now you have example 2. Okay, please look it by yourself. Okay, very easy, but you need some pondering. Okay, try to understand this. Okay, I'm sure you can do it. Okay, and I think every part of it has been clearly explained. Okay, like buoyant force equal to real weight minus apparent weight. Okay, this all I have explained to you. Okay, so this part, make sure clearly understand this. Since rock is fully submerged, okay, pay particular attention to this. So volume of rock equal to volume displaced. Okay, so imagine we have water. Now it is fully submerged, so meaning the volume displaced, the water displaced, okay, volume of water displaced must be equal to the whole volume of the rock. Okay, this part only that I think maybe slightly we oversee, terlepas pandang. Okay, this part. So make sure you go through, okay, all of this answer. Okay, now example 3 is slightly difficult, so let's do some thinking. Okay, imagine at first you have this box, and then it is not fully submerged, but it is floating. It is not fully submerged. Some of it is outside of the water, like this, like iceberg. So if a person stand on it, okay, it will cause the box to fully submerge. Okay, to fully submerge. So you are given all of this info. Okay, calculate the mass of this person. Okay, what is his mass? Okay, the person mass. Okay, so now the most important thing, first we write down the equation first. So for the case of floating, we know that buoyant force equal to weight of the box. Okay, B stand for box. Sorry, I should put box here. This one is buoyant force B, FB. So for floating, we know buoyant force equal to weight of this box. So but for this case here, when this person stand on it, now buoyant force still, because it is still floating, like this, equal to weight of the box plus weight of the person. Okay, because it is still floating, or suspended. Okay, it is float or suspended at certain depth. So but the equation is buoyant force equal to weight of the box plus weight of this person. So now we proceed. So the solution is, since all forces are in equilibrium, it is not moving here, it is static here. Okay, all forces are in equilibrium, so buoyant force plus equal to weight of box and weight of that person. So Archimedes principle states that the buoyant force equal to, okay, weight of water displaced. So how to know the weight of water displaced? Okay, so because we know the volume of the box, okay, and it is fully submerged, it means the water displaced is equal to the volume of this box, because now it is fully submerged. So it must be that the volume of the box equal to volume of water displaced. So since we know the volume of box, so we can use this formula to find weight of, or value of buoyant force. Okay, so buoyant force equal to weight of water displaced. So weight of water displaced equal to m water displaced times g. Okay, so now m equal to pv. Okay, this come from formula of density, mass divided by volume. So here mass equal to this part, okay, pv, okay, times g. Okay, now And also we know that weight of the box, okay, because the question does not give us the weight of the box, but it gives us the density and the volume. Okay, so now same thing, weight equal to, we know m mass times g, but we don't have the mass. We use this relationship, okay, density of the box times volume of the box times g. So now, therefore, we want to know the weight of the person. Since we know VB here, okay, since we know the FB here, okay, and we know the weight of the box here, okay, using this formula, so we rearrange to get weight of the person from this formula. Okay, so we just substitute all the expansion of the formula that we have done here, okay, FB here and weight of the box here, okay, so we input all the data and we get weight of the person is 2256.3 Newton. But question want us to find mass, so divide by 9.81, we get mass is 230 kilogram. Okay, maybe this is a bit difficult, but I'm sure you will understand if you go back and try to read it carefully. Go step by step, go slowly. And the most important thing, if you know how to write this equation, I'm sure there will be no problem. So that's it for today. Inshallah, I see you on Wednesday.